like last time. And as you know, we'll have the slight change in the schedule for the last day, so we can free up the afternoon. We'll have the first slot at 9:30 on Tuesday, the second slot at 11:30 on Tuesday, and then we'll have the valedictory session at 12:30. So we are done by 1 more or less. Okay. I'll keep reminding this, so hopefully it will be clear by the time we reach the last days. Okay. So yesterday we saw the an introduction to complex system science and basic concepts of this area. So one thing we saw that it is actually adopting an approach which is slightly different than what has been used in the scientific inquiries so far. Okay, it gives up, at least for the moment, a bit of the mathematical beauty of the reductionist approach, but it can possibly explain phenomena which are not really easy to accommodate with the traditional approach to science. So, for example, nonlinear dynamics, strange things like fractals, emergent behaviors, multi-scale systems. So these are all things that traditionally are not tackled or not easy to tackle with the reductionist approach, right? So we saw also that reductionist approach as compared to an emergent approach, basically the main difference is that a reductionist approach says that if you understand the components, the parts of a system, you will understand the system as a whole. But that's not what the emergent approach says. It says that basically even if you understand let's say the individual components, the resulting system is much more than the sum of the parts, or at least it's different than the sum of the parts. Okay? So today we are going to start to see how we could actually use these tools from complex system science to model networks that are of relevance to 5G. And last thing I want to remind is that when we talk about complex system science, we don't really mean a specific tool. It's more of a set of tools. Okay, so there are very few things you can do, and some of them are very formal and grounded on information theory, as we will see later in this course. Some are more simulation based and software approaches. Others are reproposition of things we know in a different context, like graph theory, which becomes now network science, or statistical mechanics, which is now applied also to study other things that it was meant to study originally. And some things have been there for a while, like bio-inspired approach, genetic algorithms, self-organizing approach. These have all been to some extent there for a while, also in ICT. So, it's few things. You'll have to pick what you need, and you might pick few things, but you have to be aware that the tools are very heterogeneous. So, if you are not very strong with information theory and math, you should not probably pick tools from that domain. If you're very good at programming, there are better tools you can pick, okay, and so on and so forth. So it's a mixture of more empirical methods and more formal methods, okay, and you will have to decide for yourself what suits you as a researcher and what suits the specific problems you're tackling, okay. So there is not a single silver bullet, okay. You have to see what you need. So the question we are going to try to answer today, at least partially, is whether the future networks can be modeled by using complex system science. So first we have to ask ourselves, what will the future networks look like, and is there anything that tells us that these networks could be potentially complex systems, in the view of what we said yesterday are the characteristics of a complex system. Yeah. So there is an increasing trend towards autonomicity, right? Things potentially should operate in a self-organizing way, in an autonomous way. So we are moving far away, at least in some aspects of new networks, from the idea that you have a central genie optimizing the network, okay, which is always the best thing to do if you are capable of doing it. So if the system size is not too big, if there is not too much signal in exchange, if the time within which you can come up with the decision is reasonable, then you should go for an optimization approach, I think, okay. Now the question is, what if the network is too big? What if the signaling you should exchange before taking a decision and the time before you get to a decision is too large? Then likely the centralized approach won't help too much, or you will come up with a decision, and by the time you actually implement the decision you came up with, this is obsolete, is out of date, because the system has changed, or simply you have to give up some precision, you know. So so again, I'm not saying that this approach is alternative to what we already do. It's complementary. So you have to decide, and that's always true. There's not a single tool that will replace anything else, okay. So you have to see for yourself whether your problem is suitable to be treated with the tools I'm going to talk about in these days or not. If not, then you should stick to other things, right? And there are also alternative approaches to this autonomous, let's say, distributed decision making. A very successful example is game theory, right? So there are other things you can do, and you know, they are perfectly fine. One difference with game theory is that game theory normally focuses on how you reach, let's say, whether you can reach an equilibrium, okay, and what the system will look like once the equilibrium is reached. It won't tell you too much about how you get there. So game theory is not good to tell you the time evolution of the system. It will tell you the final, the limit switch, in a sense, right, of the evolution. So it won't tell you too much whether the evolution is very irregular or very regular. And it's very important when you have a system, when you're designing a system, how the system operates between equilibria also, right? Because you could have a situation where it's really like simply going back and forth between states, and that's very bad for let's say, from a user viewpoint, if you're talking about communication network, right? Because it's of little use to a user if there are some periods where it's very nice, the service, but between these kind of stable periods it's a mess, right? You would immediately have a surge of complaints from your users if you would do that. So it's also important to look into how you get there. Now it's something, because also of resource constraints, you know, and knowledge, we will try to do something in the future, but we didn't work on that. But you know, if any of you is interested in studying the dynamical behavior of networks, that's probably where complex system science might do a better job than game theory, okay, if you really want to find the difference. But if that's not your concern and you want to study how you can come up with decisions in a distributed way between competing entities that might even collaborate at some point, then game theory is probably a good tool, okay. So again, I want to make crystal clear that I'm not going to sell this as the solution to all evil in the world, okay. It will be useful for some things, but probably not for others, and it's up to your, you know, experience as a researcher and of course your advisor to actually select what you need. In fact, I think it's a very much iterative approach between the problem and the tool, right? So many people start from the tool and then they look, in a sense, they have a hammer and then they look for nails all around, right? Have to nail everything because that's the tool they have. You know, I think that's not an approach I would favor as a supervisor. I would prefer that you solve relevant problems to the community you belong to, and then, you know, you select the tools based on the problem, okay, based on what you need. It is also true that it will take some time before you learn a tool, okay. Before we got some results here, it took 2-3 years, and I know people working with stochastic geometry, before they publish something with me, it took 2 years. So roughly speaking, to be familiar with the tool to the point you can publish, it takes, if you're very good, 1+ years, normally a couple of years. So it's very crucial, along with the choice of the problem, right after that you pick the right tool, right for you. Okay, it's with something you can deliver. So again, you should always consider what you're good at, not what you would like to be good at. That's a big difference. Okay, that's a common mistake. You have some aspiration to be good at something, but that doesn't mean you're good at that, right? So you have to be honest. Okay, so I think you have to be honest and see what you can do and what you know and what is easy for you to grasp. And normally you have this intuition since the childhood. Okay, for me such a thing has always been math. Whether I studied or I didn't study, it was independent, the result. It was always good, honestly, okay, without bragging about it, but it was much different with other things. About implementation, oh my God, let me stay out of a lab, which is better for the institutional thing. You know, so you have to know that, and you know that, okay. So based on that, you should pick the tool, okay. So if you are hopeless at math, stay away from information theory and to formal approaches, and you can do fantastic job with software. Okay, there are amazing approaches you can take from artificial intelligence, agent-based modeling, all sorts of things you can do with software nowadays, okay? And you can publish in some journals. So just to close this introduction, pick the tool wisely. So autonomicity is there. Think about increasingly dense networks, simple devices, many devices. Situation ever changing now. Spectrum is changing now, right? You don't have like in the past. You get your spectrum, you operate there, and then after 10 years, you might get another spectrum. So it's much more dynamic now. There are things like cognitive radio, right? Dynamic spectrum access, license shared access, and so on and so forth. So even the spectrum you use, it's very much changing dynamically. Even if you don't have this sharing regimes, by the way you operate a network nowadays is very much based on dynamic spectrum access anyway, right? Because you have the scheduler, you have the intercell interference coordinations, right? Frequency reuse. All of these things actually contribute to complicate the picture. Yeah, we have many new layers of deployment. In the past, it was more or less three things were going on in communication. Okay, there was the cellular system with these large cells. Was Wi-Fi covering a dual space in a sense, the indoor more or less, right? And it wouldn't be covered by cellular networks much. And then you would have this strange community doing sensor networks, ad hoc networks, which honestly didn't have even much of a hope to be. Well, they had some aspiration, but it didn't make it really in the mainstream. That was up to 5 to 10 years ago. But nowadays it's much more blurred, the boundary. So you start to have interworking between networks. You start to have different levels of deployments, right? Small cells and bigger cells and so on. You start to have even the MANET, VANET that are coming back to in some sense with scenarios related to emergency communications, transportation. So it's everything blending in a sense. Okay, it looks like a bit of a magma, okay, of things. And there is a surge of distributed topologies, Cloud RAM, massive distributed MIMO, and in any event, you always have the tendency to push the intelligence towards the edge. Like, so small base stations should decide for themselves. So all of this picture makes us think that there are some characteristics of future networks or currently evolving networks that are resembling those of a complex system. Okay, if you remember what I said yesterday, some of the things I'm saying here would kind of ring a bell, right? You still want your decisions to be not too global so that you don't spend all your life coordinating. So it has to be there has to be some level of locality in the way you decide, but yet you want all your network to work, right? You don't want to have islands of bad service and so on. So if you want to operate a global network, you have to honestly give up on the concept of centrally optimized things, right? That doesn't mean, though, you have to give up on it completely. It can also be a mixture, right? Again, one mistake that was done with ad hoc networks was to propose them as an alternative to cellular systems, and that didn't work out, okay? It's much smarter idea to complement things that work. So the networks as they are right now, they work, okay? So if you want to propose new things, they should integrate. So you can always have some more centralized traditional optimization approach, okay, maybe at a higher level, and then you decide locally what to do. So you limit, you would have a cluster representant, right, of a certain region, and then the different clusters would communicate. But then locally you would do something else. Or you could have a hierarchical approach, central and central and central, right? So it's more complicated than just say I'm doing everything centralized or everything distributed. Most likely the reality is in between. My rule of thumb, it depends also a lot on the density of deployments, okay? Because eventually nodes are the ones that matter in terms of transmission. If you have too many nodes, you probably have to give up on centralized approach, okay? Now, what we try to do in our work is to model future networks by mapping them into an abstract model. And we see basically networks as collection of black boxes taking local informed decisions. So these black boxes potentially could be anything. Could be a base station, could be a user, could be a network. Okay, much of the tools we are using are independent of that. So then it will change the way you model, say, for example, the interference between these entities. Okay, how you model the aggregate interference and so on. But the models per se are not limited to this or that scenario. Okay, it's up to you how you want to fit your scenario using the model. So as I say, each black box could potentially be a network on its own. Okay, and the example we are going to consider today is one of the examples is frequency assignment. Now, historically, because of what we do in our group and the trends, we have been focusing quite a bit so far in the complexity track on frequency allocation. But stay away from the idea that that's all you can do. In fact, we have plans now in the collaboration with Professor Das to go beyond this and to adopt, to actually apply what we are doing to other functionalities. It doesn't have to be frequency allocation, okay? So what I'm going to show today is just an example. And in the next days, we are going to see another completely different example of application, an IoT network managing the road traffic or sensor network. So nothing to do with what we are going to see today. So just to show that the different problems you can tackle are very heterogeneous. Okay, but you have to start from somewhere. So we decided to start from frequency assignment. Now, another thing is that, yeah, as I said, like the future world, all the networks will be possibly all networks will be self-organizing entities. The predominant mode of access of to the spectrum is dynamic. That's what it looks like, at least. So what we will explore is whether the behavior of a collection of cognitive autonomous self-organizing systems can be treated as complex, and what it means exactly to be calling it complex. And whether we can use complex system science to possibly shed some light on how to design and deploy these networks. Okay, so there are a few things we are trying to do. Basically, there is a scientific endeavor here to understand things, okay, but then eventually we are engineers, so we hope ultimately to be able to use the insights we get from the scientific study of the networks to better design and operate networks, and probably possibly to give hints on how to deploy future networks. Okay, so we are still not there. We're working towards that, but I think this program of research should be complete at this stage one, when we can have the loop to be closed. Okay, so where we do understand something that gives us some idea about how to change the network, and then we test it and we see whether the network got better in some sense. So the first step of what we want to do would be modeling the network, okay, basically. The second step would be identifying the links between some characteristics of the system or quantities in terms of complex systems, and then the traditional things we are used to: throughput, coverage, energy efficiency, and so on. Okay, we are working on that at the moment. And the last bit would be, once we identify the links, hopefully we could use the complexity or other complex system science metrics as a knob. Okay, so we are studying, for example, we want to see what is the correlation between these new kind of metrics and the old ones, in a sense. And possibly, if the case is that we have a high correlation between one of these new metrics and many of the old ones, you would not have to worry about multi-objective optimization of all these things. You just tune your control, in a sense, okay, in terms of complexity. This is some of these speculations. For some of these we have some results, but the idea is to try to test this assumption. Now, many things can be done, and it's useful anyway as a modeling tool, okay, this complex system science. There are many things you can do and understand. So even if, say, the more ambitious ideas about how to control a network would fail, we would still have a nice understanding in the scientific terms, okay. We would enrich our understanding of future networks. That I think is true anyway. So the first specific application we see is how to tackle the problem of self-organizing frequency allocation. And I just want to recall what a complex system can be defined, how a complex system can be defined. So it's an ensemble basically of simple agents that interacting with each other achieve a non-trivial, i.e. complex behavior. Now, there is a bit of a catch, because to define a complex system, use the complex word again. So it's like circular definition, so it's not so useful in a sense. But you see the field is emerging, so there is not like a clear-cut mathematical definition. There are though some quite precise ways to talk about complexity. The problem is that we don't have one, we have many. Okay, so there are many ways to define complexity formally. Some are better than others, in my opinion, but it also depends on what your goal is. So depending on what system you are looking into and what you are looking specifically to understand of this system, you should pick one complexity metric or another. Okay, but there is not one thing. It's not like mutual information, which is one. There are a few things. So today we are going to see one example of how we define complexity. And we will basically model each autonomous network as a cell in a lattice. And this network, or whatever black box, okay, doesn't need to be a network, it can be a base station, honestly it doesn't matter. It will follow a simple set of self-organization rules, and then hopefully you'll get something good out of it at the global level. Okay, any question or comment? Nope. So we are claiming that the system we are considering in this specific case will turn out to be complex in terms of entropy and complexity metrics. So we are going back to that. And the simple agents we are considering will achieve a non-trivial interference-free or interference-limited frequency allocation. So this hits actually two targets in terms of how we define a system to be complex. So first of all, there are some characteristics of complex systems in terms of the values of entropy and complexity. Okay, we are going back to that. And you have to be in a certain region for entropy and complexity to be calling the system complex normally. And another thing that characterizes a complex system is that simple agents which take local decisions will give rise to a pattern leading to some optimal output, whatever it is. In this case is interference limitation, which is not something you could just come up by design. So what I'm saying is that the traditional approach, for example, to frequency to interference management via frequency allocation is that you kind of have an intuition that if you space far apart the cells which use the same frequency, and you repeat this regularly, like this kind of frequency reuse patterns, that's more or less the best you can do. Okay, so the approach here is completely different. You try out some simple and intuitive roles at the local level, and then you let the system go, and you see what happens in the end. Okay. We are going to consider cellular automata specifically to model this, and I'm going back to cellular automata later in the course, so don't worry if not everything is clear at the moment. Now, one thing I have to say though, you have to apply some smartness in the way you define the local rules. Not every local rule will be equally good, right? So there has to be some intuition about the behavior which makes sense. So if you are picking which channel to use, you should possibly check what the neighbors are doing and try not to mess up with them, right? You just count, for example, if you have a certain amount of channels available, you check how many neighbors are using each channel, and you should pick the one which is used the least. As simple as that, okay? Not much more than that. And even with these very simple approaches, you actually lead with some smaller, complications. You lead to a very nice general set of, a very general and global outcome. And that's very simple. So no matter how easy is your optimization, it cannot be that simple, right? So the idea is that you might not even get maybe as good. Well, in some cases here we get, but in general you might not get as good as you would get with the optimization if you could do it, but good enough. And the point is, in some cases you cannot do optimization anyway. It takes too much time before you get a decision, right? And we have actually two scenarios. One in which we use cellular automata, which is an abstract, in a sense, abstraction of the network. And then we have another scenario where we actually simulate more, we actually take into account more accurately interference. So this is going to be based on an LTE system level simulator. So we are trying to show that it's not just the toy mathematical model that works, but also the more realistic model will give good results.
Sir,
yes.
Actually, yesterday you mentioned that in a complex system there should be a feedback path.
Yes.
So here,
yeah, I mean, it can be there, okay, and it's probably a good idea. It is there. I think here you get some feedback in a sense from the environment because you adapt, okay. So you basically observe the environment, you take some decisions, we change the environment. So in a sense, you could also consider the environment itself as a form of feedback, right? You basically have that as almost as a player itself, right? So you can have that. We have other works where we consider exchange of signaling and so on. Not in this work though, okay? This work is like more, you observe the environment and then you take a decision. So it's kind of open loop in the traditional sense, but it's very important that you consider that you adapt to the environment. So in a sense, you do have some form of interaction with something, right? So it's not that you are just acting obliviously to everything. Okay.
But traditional wireless network has a feedback in terms of maybe channel quality indicators.
Yes, yeah, you can do that. I mean, here, for example, we do have. In the second example, there is this more traditional way of doing feedback. So we check the SINR of the users, and then we try not to dissatisfy too much our users. So you have to get, but these are kind of things that are there anyway, right? So of course, if you have available some additional information, you should always use it. Okay, so yeah, I think it is there. What is added? Probably there's a very big importance here in the not just of the interaction with your, let's say, users. Also, you have to have some sort of interaction, at least indirect, with the neighbor cells or systems. And it's always very important that you check the environment, okay, and you try to adapt to how the environment changes, okay.
That's how this communication works, I think, from the environment.
Well, it's again, you basically, okay, the environment is what it is, and then you take some decisions, okay, which will impact the environment, and then again, you see, it's kind of a loop, right? So, and that's true for any adaptive system, really, right? So, the concept of normally you would have another transmitter, right? And that would be what we define feedback. But if you look at it, even the environment itself indirectly is interacting with you, right? So, in fact, I think in much of the work in complexity, you do consider the environment itself as an entity, right? Yeah, question? Nope. Okay, so we have a couple of papers on this. I'll try to give some idea. Okay, I think for the sake of time, I'm not going into too many details. I'm just trying to give you some gist of how the things work. So you do have each of these squares represent a system. Can be a network, can be a base station. If it disturbs you to consider it a network, consider it as a base station. Doesn't matter really. Okay, and then basically you will act at different times. So you start from time 0 in a random place, and then you have different ways you can model the neighborhood. For example, there is the von Neumann neighborhood where you consider a cross. So the neighbors are only the very closest neighbors. So up, down, east and west. Or but you could also have the Moore neighborhood, which is the first ring around, right? So, and depending on that, you will get different solutions to the frequency allocation problem. So basically for Neumann one, as far as I remember, is trivial because you just have to alternate frequencies. Okay, so a couple of channels are enough. I think you just put it in a checkerboard way, right? Because you can always have a certain frequency in a square, and then you just put the 4 closest neighbors with another frequency and so on. So a checkerboard would do the job. It's very dull. So we checked that just to see that things work, but we didn't focus on that because there is not much to learn there. The Moore is more interesting. It gives rise to things like evolution of basically the way you activate cells evolve according to concentric squares. Okay, so it kind of propagates as a wave, and then you will basically do something. You will pick a channel which has not been picked by cells which have changed their state in the current and former slot. Once you decide on the channel you use, you will then keep silent for 2 time periods just to avoid, you know, ping pong effects and so on. So there are some things you can do. Now, in this case, for example, you see that in general, actually, because of the kind of concentric square evolution in time, at most you will have to take into account 5 neighbors, right? Or if you're lucky, you're in the corner, 3, right? So either you are in the corner of the square or you are somewhere else. If you are somewhere else, you have only you have basically 5 neighbors. If you're in the corner, you have 3 neighbors, right? That's the square. And so therefore you will be okay with 6 channels in this case. Okay, so that's why, for example, we consider 6 channels in this case to cover this network. Okay. Yeah, so I think, you know, it's difficult without spending really proper time to present the paper and so on to tell you the details. I hope I gave you some understanding. If you want to understand really well the thing, I have references and you read the papers, and that's a better investment of our time. Okay. Roughly speaking, it works as I told you, but you know, you have to read the papers, and then we have some theoretical analysis, and we have, you know, the algorithm explanation step by step. So that's a better idea, I think. Okay. So what happens then? Okay, so we showed basically, okay, we are going back to this example anyway in this course, but we showed that you can achieve with cellular automata these very simple rules about checking what the neighbors do and not doing the same, possibly. You can actually have an evolution of your network which is interference free. The way we define interference here is simply checking how many neighbors are using our channel, which is a simplified way, right? So it's just a discrete interference model. So we are happy when nobody in a certain cluster uses the same channel, and we could achieve that. Okay, so we have results about that. We will present later a model which is more realistic, which has a real path loss model, okay, and shadowing. So it will show basically a more realistic version of interference, okay, more continuous as it is. So what we did then. Okay, first of all, there are 2 things we want to achieve here. One thing is that, as we said, to see if a system can really be called as complex in this context. One thing is whether with simple rules locally applied, we can achieve a global behavior. But that we could see. Okay. The second thing is to calculate some precise metrics for entropy and complexity and see if we are in the right region for a complex system. And that was the aim of this couple of papers we wrote on this topic. Okay, so we did use a metric for complexity which is called excess entropy, and we combine it with the entropy you are used to. There are some differences, but if you took an information theory class, you came definitely across the concept of entropy. So it's the same thing we are using here, and there is a difference though, in the sense that the entropy you saw most likely is going. It had to do with basically unidimensional situation, right? So you basically consider a string of symbols in time, right? It's a random variable, basically, and then you calculate the entropy. Here we are actually checking the entropy of a 2D system and not to do with symbols. So entropy is a general concept. You can apply it to whatever you want, as long as it makes sense. So here we are checking, in a sense, we take a snapshot of the frequency allocation, right? Which channels is used everywhere, and then we calculate the entropy on that. You can do it because you can generalize the concept of entropy to a 2D situation. So in the 1D case, you condition, basically you can define conditional entropy, condition on the past symbols. Now here there is no time, so it doesn't make sense to talk about past, but we talk about half of the plane. So you condition what happens based on, right, some half of the plane. So it's a generalization of the concept of entropy, basically. So you define a template and you add basically, so you take a cell of interest, which is X, and then you add neighboring cells according to a certain way, okay? So you do add first in this direction, and then in this, and then in this, and then again and again, like that, until you cover all the half plane you're interested in, okay? You see, you could say basically that you will have a certain line divided the plane here, right? So that's what you're doing. Now, doing that and taking the limit, so this M is how many cells you had in your template. So taking the limit to infinity, you end up with a certain asymptotic entropy, okay? This is small h. And then what we do for templates that are going from 1 to infinity, we subtract the value of entropy for a certain finite template minus the limit. So we have this limit entropy, which is there no matter what. It's kind of, if you want, the intrinsic randomness of the system, right? Nothing you can get rid of. That's the system itself that leads to this randomness. But for smaller templates, it's simply ignorance. You don't know enough. So your entropy will look higher than it actually is, okay? And then if you take enough, well, sometimes it's not that you have to go that far, M equal to 6, okay? If you take enough cells in your template, you will reduce this ignorance to the minimum possible, which is, again, the intrinsic randomness or entropy of your system, okay? So we are basically kind of explaining away the randomness in a sense. So this kind of histogram or area between the apparent randomness and the intrinsic randomness is what we call excess entropy, okay? In our paper, we refer to a physics letter which introduced these concepts, and I think if you're interested in this, it's not enough that you read our paper. You should also go and read that paper, because we base our theoretical quantities on that. So you have to understand that first. Even though it's a physics paper, it's very well understandable. It's nicely written. And actually, the scientist that wrote that paper is a physicist who is one of the investigators of the Santa Fe Institute. Well, again, this very famous institute for complex systems comes back. They do very good work. Okay, so eventually, again, I don't want to kill us with details. Okay, I hope I gave you some general idea, but you have to go into the papers and spend some time if you want to understand better. We can calculate these quantities. Okay, now what should happen in terms what we want out of this? We hope that some understanding of the structure that emerges from the lattice will be there. Okay, yes.
So basically, in communication system, entropy is defined as the average information per symbol.
Yes.
So in this case, how would you define it in simple terms?
Yeah, again, I think now with the understanding we have of entropy, it has to do with a specific, application. Entropy, though, is a more general concept. Okay, so it basically it's a mathematical operator in a sense. Okay, you can calculate to understand the randomness of a system, basically, right? So now, according to Shannon theory, the highest amount of information is when you're most uncertain, right? So when you flip a coin, if the probabilities are same, you get the highest possible entropy for that system, right? Problem is that that's not always very telling. Okay, it has been very successful for our systems, and it led to coding theory and so on. But that could lead to things like, is it always true that the random system tells you a lot? I think it's not always so true. I mean, if you look, for example, to a problem like frequency allocation, you want to stay away from a random allocation. You see my point? So depending on what you have to do, you have again to maybe redefine the concept. So entropy is good in a sense. We understand whether we are in the right region for complexity, but complexity to us is more useful, okay? Because randomness or entropy is not necessarily a good thing. Depends, okay? So if you can do, I mean, normally when you come up with any allocation scheme, you benchmark with randomness. Randomness is going to be the sloppiest thing you can do, right? So it cannot be what you aim for in a sense. So here we take it as a quantity. We basically check, okay, but it's not our aim to maximize entropy. In fact, there is a definition of complexity which is very famous, called Kolmogorov complexity, which exactly tells that. Basically, we're going back to this, but the Kolmogorov complexity defines complexity in a way that is the shortest description of a program solving a problem. I'm telling it very, very roughly now, okay? And therefore, basically, if you have a random, say, string, there is no program that can do better than just copying the string, right? There is nothing that you can use to compress. So the description is going to be as long as the random pattern. On the other extreme, you have things like constant patterns. In that case, it's the simplest thing you can do according to Kolmogorov, because you say 1, 1, 1, 1, 1. What do you say? Can you come up with a description here which is very efficient? It's 1, 1, 1 forever. What would you say to a computer that has to print the string? You have to code it. 1 forever. 1, 1, 1, 1. You want to code something, an algorithm which prints out this string. How would you code it? And print 1. Period. Right? Not really mind-blowing, right? So, but for a random thing of which you have no clue about the evolution in time, what can you do? You just read it and repeat it, right? So that's again, you see that's another approach which is kind of aligned with the Shannon theory, but again, doesn't really make much of a difference to a telecom engineer in some aspects, okay? Because he would encourage to consider that it's more complex or more interesting to look at random things, which in some contexts is true, some other is not, okay? So we did plot the excess entropy and so the complexity, say, which we use in the context of excess entropy here, and the entropy, and then showed what happens if you start to change the ratio of active cells. So increasing P means that you are increasingly switching off your network. So if P is 0, all the cells, say, are active. If P is 1, all the cells are inactive, and then the other cases are in between. So if you see, for example, in a regular case where P is 0, you start for a regular allocation. You start from a case where you have excess entropy, so complexity and entropy are 0. A regular case would be, let's say, if I have a figure, not here, I have it somewhere though. I have to go here. Yes. So basically, the regular case would be something like this. So you have 6 channels, because you need minimum 6 channels, we said, and then you replicate, right? You repeat the pattern. That's what we do with frequency reuse normally. So if you actually calculate the entropy and complexity of this guy, we'll have 0 in both cases. Why? Because entropy tells you how random a system is. This is very far from random. It's actually the opposite. It's completely irregular. And it's not complex, because complexity, again, take it with a grain of salt. It tells you how intelligent is the structure you're seeing. So there has to be a structure, and there is a lot of structure here, but it's very dull. It's so dull that once you know 6, you know a template as small as 6, you just copy that forever and you'll get the understanding. So it's very dull, right? The random case is actually the opposite. So you do have relatively high entropy, and you do have a complexity of 0. Again, because there is no intelligent structure whatsoever here, right? Nothing really that tells you there is any intelligence there, right? It's a random thing, and the entropy is maximum as it should be. Now, can anybody identify there is a specific reason behind this specific value? Anybody guessing from your memories of information theory classes? We have 6 channels here. So what is the highest value you can get in terms of entropy? If you have 2 equally likely outcomes, what is the highest value for entropy? It's 1 bit, right? Log 2 of 2. If you have 6 possible equally likely outcomes, log 2 of 6, which is 2.58. Makes sense, okay? And then you have the situation in between, which is based on this self-organizing local informed scheme I was trying to explain before, which gives actually the values of complexity which are higher than 0, definitely, and an entropy value which is in between, which if you open any basic book on complex systems, would tell you that that's where complexity is. It's definitely, okay, you have to check the complexity value, but another value that tells a lot is how is entropy. So in a sense, a complex system should be almost at the middle point between complete order and complete disorder. So they call it the systems of organized complexity, and that's where you want to be as a complex system, okay? Okay, then we check the evolution. Practically, if you start to, let's say you start from this case of the regular allocation of frequencies, you start from 0, 0, which is what we expect. Switching off basically base stations or cells would lead you to an increase of both entropy and complexity, because you are making the situation less dull and also a bit more random, up to some point where you kind of go back, because I mean, if you have all the networks switched off, it's again a very regular structure. In fact, all of these different situations, no matter where you start from in terms of allocation, if you switch off all the network, you have again a super regular network, right? It's as regular as a checkerboard, correct? I mean, there's no randomness there, and completely structured, right? But dull. Okay, and then you have the random case. You start from the highest possible value of randomness, and the more you go towards the case of a completely switched off network, the more you get away from the random case, right? Up to the point you're completely regular when the network is all switched off. We all on the same page? Yeah? And then you have the self-organizing case, where you start, you see, at a high value of complexity and somehow intermediate value of entropy. And then, of course, that's the best you can get in terms of complexity, okay? If you start to mess up with your network, switching off parts of it, you cannot get a higher value of complexity, but you might get a higher value of randomness, up to the point, again, where you are in the region where the network is completely shut down. So entropy is 0 and complexity is 0, okay? Never complex. This is observation, so we do have some explanation, but I don't know if they're completely satisfying. Let me check what we said about the random assignment. Yeah, I mean, honestly, the only thing we observed in the paper is that the entropy decreases as we would expect, because you get you get more and more close to a regular situation when you shut down the network. However, probably because you start from a completely messed up allocation, you're never going to get better off in terms of complexity. But this is kind of, we don't have a theory for this. This is an observation. We just wanted to see if things make sense, okay, in terms of the complexity and entropy trajectory. It's also nice to see the things. Yes. Yes. I think this is not probability 1. Okay, we stopped a bit before, if I'm not wrong. This is 09T. Yes, if you go to 1, it must go to 0. Yes, of course. Because eventually with 1 they are all the same. So they have to be all in the same point, right? It's like a black network in a sense, right? Completely shut down. Yeah, I suppose, you know, where you start has a lot to say about complexity. So if you start from a case which is irremediably flawed, right? It's completely random. It's not that by switching off networks you get any intelligent structure, right? You will get to a case where there is eternal peace in a sense, right? So, but no complexity, of course. Okay. So the best you can hope for is to go towards a restful situation, but nothing good will come out of it. It's like when you, to make a bit dark metaphor, it's like when you suppress a rebellion. It's not that you come out of the suppression with a very nice and peaceful society, right, and very positive. But at least there is no fight ongoing anymore. But the initial point was so bad that it's not that by doing some intervention you'll come up with a nice society, right? Okay, so we try to see something. Okay, now it's still in terms of the scientific domain, it's the analysis, the modeling, right? Okay, how does it look like? We tried also to see what happens in terms of some more useful characteristics of the networks for an engineer. So, for example, if you disrupt the allocation and you change randomly one allocation in a certain cell, how does it actually turn out to be in terms of robustness? So what we mean by robustness here is that, okay, you do your experiments, you change the value of the channel, the channel you use in a certain cell, and then you optimize, you run an optimization problem, you solve an optimization problem, and you check how far you are in terms of number of changes needed to get to an interference-free situation. So this is like, we just run different realizations of the allocation, and then we check for each cell, we check for each possible channel, and then we come up with the probability. We just measure how likely it is that starting from a certain situation you can end up in a positive situation. And this is completely probabilistic. So we don't have an algorithm doing that, we just check how far you are. And the distance here is just the number of changes required. Okay? So when we say probability C equals 0, it means that you have no change to do. So even if you change the specific channel used in a certain cell, that is still okay, because the structure you came up with is actually robust in that sense. Okay, because is not impacted by this. So the probability of a number C which is greater than 0, it means you disrupt the allocation and you would need to change something, right? So it's not enough to just leave it there. And then we compare the centralized planning, okay, where you have this pattern repeating itself, and then the self-organized algorithm. And the radius simply means the radius of interaction. So we allow actually changes within a certain radius. So we don't allow changes everywhere, just to have some control on the situation. So radius 1 would be the first tier around the cell, and radius 2 would be the first 2 tiers. So probability of no solution, in the case you have a radius of 1, so basically you cannot, no matter what you do, end up in an interference-free situation. It's actually better looking for the self-organized case. So it's half, basically, 0.2 more or less against 0.4. The probability which is the ideal, where you have no change to do whatsoever, is basically better for the centralized case, but not so much better. And then the situation gets interesting, because basically in general you require less changes in the self-organized case than in the centralized case. Okay, for example, here if you check this case r equal 2, you see that the probability that you need more than 4 changes is 1 minus this sum, so it would be 0.08 in this case, but in this case it would be 0.4, right? 5 times higher. The probability to need more than 4 changes. So there is some intuition that actually that the self-organized case is more robust. Again, this is a probabilistic study with all the limits of the case. We don't just show that we can actually do it. We just show that the distance to an ideal situation is closer. And again, it might not be the most intuitive part of the lecture, so we do have a Springer journal where we do explain this in detail, also what we do in terms of the optimization problem. Optimization, by the way, is not to solve anything. Here we are just checking. We run an optimization problem to find out these probabilities. That's all. We use it as not as a design tool, but as an analytical tool in this case. Okay. Anyway, the details are there. We have a couple of pages, if I'm not wrong, on this, so it's more than a slide. Okay, so you have to check that, and if something doesn't sound very intuitive, you let me know. But you have to read the paper. Okay. Okay, then we check with the more realistic scenario where you basically have not these ideal square cells. You really have like LTE cells with proper channel model and proper user distribution and so on. And we just double check that if you do, we have some sort of self-organizing algorithm, very simple again, very local. You just check, basically it's based on the SINR of the worst, let's say the worst SINR of your user. Okay, so maybe I can give you some details. So it's first of all distributed. Okay, you do rely on local information, so what you see in your environment, but you don't have inter-cell transmission. It's very completely distributed actually. There are two parts: an initialization phase where you pick one of 5 available channels with equal probability, so you just have to start somewhere. We take 5 because there are these 5 times 20 megahertz frequency channel allocation in LTE. That's LTE advanced, just as a number, doesn't matter. And then you have a second phase, which is a channel selection phase, and you decide whether it's necessary to switch the channel you pick randomly. And if so, which channel you should choose alternatively. Basically, the switching is triggered if the SINR of the worst receiver in the cell, so the worst SINR, the worst user SINR, it's below a certain threshold which you set. Okay, if that's the case, it means you are in an outage situation. Okay, you can define the outage as you want, but that's what we did. And if you are in outage, then you have to switch channel, and you will choose the channel on which the majority of the receivers experience an SINR higher than the threshold. Okay, so if you have a case where 20 users are higher, on a certain channel, 20 users have an SINR higher than the threshold, and another channel where you have only 15, you should favor the majority of your users. Okay, so you check whether the worst user is in trouble, which whenever you define the outage, you are always kind of looking for the bad guys, right? The unfortunate guys. So if that's the case, what you do, you try to find the majority of your users. Okay, and that's to test that. Again, I want to emphasize our goal here is not to propose another self-organization algorithm. There are gazillions. Okay, they come 1 million a dime more or less, so it's very cheap. Okay, we just wanted something more real than the cellular automata and see if it still makes sense. It does make sense, of course, in terms of a SINR. Unless we were really dumb with our algorithm design, you should get a better CDF of a SINR, and that's just a check, honestly, more than anything else. And it's more interesting to see what happens in terms of entropy and complexity. So is this entropy and complexity still going to be something like we saw before, or was it just an artificial consequence of an artificial model? It turns out to be the case that if you do self-organized and random assignment in these very random deployments, you do have a situation where the random deployment again has a complexity of 0 and an entropy which is high. Now the value has changed. Why? Why is it 232 instead of 258 now? We have 5 channels here. So log 2 of 5 is this guy. Yep. And the self-organized case, you see higher complexity and lower entropy. So sort of, makes sense again. We don't have a centralized assignment here. Any clue why? If you look at the deployment, okay, these are the cells, and these colors are the channels, but this represents the deployment we are testing. Any clue how to do centralized assignment here? Would be welcome if you know it. I don't know how to do it. You have to have a very regular structure, right, to have this template. I mean, how do you define a template of some repetition here? I don't know. So we we gave up on that because it might not simply make sense. So you see, that's just a very intuitive idea that if you start to use these centralized approaches based on frequency reuse, good luck with that. It's not even that it doesn't work. You can't even think how to do it. Okay, so you have to start to do something else than this, and that's something we already know probably. There are works suggesting a probabilistic way to do frequency reuse, right? So you have to get away anyway from the idea that you have this template which you repeat, right? That's not what you do here. I'm almost done. Okay, so finishing up on this. Basically, if you do adopt, for example, a self-organized approach to frequency allocation, it makes sense to talk in terms of complex systems. Okay, that's our main message here. If the frequencies are managed in a centralized fashion, no big surprise that there is no point in studying the things with complex systems because the complexity is zero. It's kind of the other end of the spectrum. If you do things in a centralized way, you will not give rise to complexity. You have to remember this emergence thing. The emergence is all based on local interaction. If you have a genie telling everybody what to do, that's not a complex system. Might be complicated, but it's not a complex system in the way we mean. Because the complex system has to do with few things like autonomous decision and so on, but in essence, the interactions are very important, and how the local interactions turn out into a global pattern. If you have a top-down approach, forget about it. If you have a bottom-up approach, or you need a bottom-up approach, then there is hope that these things we are talking about might be useful. Now, what is the relevance, apart from this almost random example we picked to show some results? What is the relevance for these things in the future? Well, there is a trend towards distributed networks formed by simple devices that still have to fulfill non-trivial global QoS requirements, right? You still want your network to work fine, but you have a lot of these new things coming up. Small cells, RFID, sensors, machine type, ad hoc, Wi-Fi, you name it. They're all kind of together now, right? There is a high dynamicity. We didn't tackle this, but it's a big part of complex systems. So there is a lot of variability, both in time, both in frequency and in space with respect to time, right? You have dynamic spectrum access. You have these beams, right? Beam tracking and beam forming, which sweeps, right, a certain area, and then you're sharing the spectrum with radars, which again, right, sweeps. They sweep basically a certain region. So there is an added variability of the situation of the channel in frequency and space as compared to what we are used to, right? You will probably need, because of these very heterogeneous and dense environments, to give up on the idea that you can optimize things, at least to some extent. And there are good examples in nature where things work very fine, right? Flocks of birds and stuff like that, where really you don't have a boss, right, telling in the morning we will fly that way. They go, and then they come up, right, with the right pattern. So why not mimic that? And there's been a lot of work, by the way, in these bio-inspired approaches already. So another thing is that most of the fundamental designs of our networks have so far been based on information/entropy. But what we claim is that, well, we still have to tell a lot about the design, but there is some evidence. First of all, that complexity tells you something else. So scientifically, it enriches the picture you have. We are actually running studies at the moment, which are under review or will be soon submitted, where we calculate the correlation of complexity with other graph theoretical metrics. Nothing to do. So it's a new thing. Okay, it's a new thing, at least in the networks we are used to. It's not. It doesn't tell the same story, and the hope is that besides enriching the picture, it also tells you how to run your networks better somehow. And we already saw, for example, if you could have a more complex network, it would be more robust to changes. We saw that. Okay, so that's the first example that things might work fine. We hope to do more, also in collaboration with Professor Das' team. Okay, that's the plan at least. So more in terms of techniques we test, and more in terms of the link to telecom metrics and possibly design. So that's the plan for the next few years. And that's it, really. Any question or comment? and we are going more into the detail of complexity metrics. So we see that it's much more than what I showed here about excess entropy. There is a galaxy of complexity metrics